Artificial Intelligence Part 1. Artificial intelligence (AI) is the mantra of the current era. The phrase is intoned by technologists, academicians, journalists and venture capitalists alike. As with many phrases that cross over from technical academic fields into general circulation, there is significant misunderstanding accompanying the use of the phrase. But this is not the classical case of the public not understanding the scientists. Here the scientists are often as befuddled as the public. The idea that our era is somehow seeing the emergence of an intelligence in silicon that rivals our own entertains all of us, enthralling us and frightening us in equal measure. And, unfortunately, it distracts us. There is a different narrative that one can tell about the current era. Consider the following story, which involves humans, computers, data and life or death decisions, but where the focus is something other than intelligence in silicon fantasies. When my spouse was pregnant 14 years ago, we had an ultrasound. There was a geneticist in the room, and she pointed out some white spots around the heart of the fetus. "Those are markers for Down syndrome," she noted, "and your risk has now gone up to 1 in 20. She further let us know that we could learn whether the fetus in fact had the genetic modification underlying Down syndrome via an amniocentesis. But amniocentesis was risky. The risk of killing the fetus during the procedure was roughly 1 in 300. Being a statistician, I determined to find out where these numbers were coming from. To cut a long story short, I discovered that a statistical analysis had been done a decade previously in the UK, where these white spots, which reflect calcium buildup, were indeed established as a predictor of Down syndrome. But I also noticed that the imaging machine used in our test had a few hundred more pixels per square inch than the machine used in the UK study. I went back to tell the geneticist that I believed that the white spots were likely false positives, that they were literally white noise. She said, that explains why we started seeing an uptick in Down syndrome diagnoses a few years ago. It's when the new machine arrived. We didn't do the amniocentesis, and a healthy girl was born a few months later. But the episode troubled me, particularly after a back-of-the-envelope calculation convinced me that many thousands of people had gotten that diagnosis that same day worldwide, that many of them had opted for amniocentesis, and that a number of babies had died needlessly. And this happened day after day until it somehow got fixed. The problem that this episode revealed wasn't about my individual medical care, it was about a medical system that measured variables and outcomes in various places and times, conducted statistical analyses, and made use of the results in other places and times. The problem had to do not just with data analysis per se, but with what database researchers call provenance broadly. Where did data arise, what inferences were drawn from the data, and how relevant are those inferences to the present situation? While a trained human might be able to work all of this out on a case-by-case basis, the issue was that of designing a planetary-scale medical system that could do this without the need for such detailed human oversight. I'm also a computer scientist, and it occurred to me that the principles needed to build planetary-scale inference and decision-making systems of this kind, blending computer science with statistics, and taking into account human utilities, were nowhere to be found in my education. And it occurred to me that the development of such principles, which will be needed not only in the medical domain but also in domains such as commerce, transportation and education, were at least as important as those of building AI systems that can dazzle us with their game-playing or sensorimotor skills. Whether or not we come to understand intelligence anytime soon, we do have a major challenge on our hands in bringing together computers and humans in ways that enhance human life. While this challenge is viewed by some as subservient to the creation of artificial intelligence, it can also be viewed more prosaically, but with no less reverence, as the creation of a new branch of engineering. Much like civil engineering and chemical engineering in decades past, this new discipline aims to corral the power of a few key ideas, bringing new resources and capabilities to people, and doing so safely. Whereas civil engineering and chemical engineering were built on physics and chemistry, this new engineering discipline will be built on ideas that the preceding century gave substance to, ideas such as information, algorithm, data, uncertainty, computing, inference, and optimization. Moreover, since much of the focus of the new discipline will be on data from and about humans, its development will require perspectives from the social sciences and humanities. While the building blocks have begun to emerge, the principles for putting these blocks together have not yet emerged, and so the blocks are currently being put together in ad hoc ways. Thus, just as humans built buildings and bridges before there was civil engineering, humans are proceeding with the building of societal scale, inference and decision-making systems that involve machines, humans and the environment. Just as early buildings and bridges sometimes fell to the ground, in unforeseen ways and with tragic consequences, many of our early societal scale inference and decision-making systems are already exposing serious conceptual flaws. And, unfortunately, we are not very good at anticipating what the next emerging serious flaw will be. What we're missing is an engineering discipline with its principles of analysis and design. The current public dialogue about these issues too often uses AI as an intellectual wildcard, one that makes it difficult to reason about the scope and consequences of emerging technology. Let us begin by considering more carefully what AI has been used to refer to, both recently and historically. Most of what is being called AI today, particularly in the public sphere, is what has been called machine learning (ML) for the past several decades. ML is an algorithmic field that blends ideas from statistics, computer science and many other disciplines, see below, to design algorithms that process data, make predictions and help make decisions. In terms of impact on the real world, ML is the real thing, and not just recently. Indeed, that ML would grow into massive industrial relevance was already clear in the early 1990s, and by the turn of the century forward-looking companies such as Amazon were already using ML throughout their business, solving mission-critical back-end problems in fraud detection and supply chain prediction, and building innovative consumer-facing services such as recommendation systems. As datasets and computing resources grew rapidly over the ensuing 2 decades, it became clear that ML would soon power not only Amazon but essentially any company in which decisions could be tied to large-scale data. New business models would emerge. The phrase data science began to be used to refer to this phenomenon, reflecting the need of ML algorithms experts to partner with database and distributed systems experts to build scalable, robust ML systems, and reflecting the larger social and environmental scope of the resulting systems. This confluence of ideas and technology trends has been rebranded as AI over the past few years. This rebranding is worthy of some scrutiny. Historically, the phrase AI was coined in the late 1950s to refer to the heady aspiration of realizing in software and hardware an entity possessing human-level intelligence. We will use the phrase human imitative AI to refer to this aspiration, emphasizing the notion that the artificially intelligent entity should seem to be one of us, if not physically at least mentally, whatever that might mean. This was largely an academic enterprise. While related academic fields such as operations research, statistics, pattern recognition, information theory and control theory already existed, and were often inspired by human intelligence and animal intelligence, these fields were arguably focused on low-level signals and decisions. The ability of, say, a squirrel to perceive the three-dimensional structure of the forest it lives in, and to leap among its branches, was inspirational to these fields. AI was meant to focus on something different, the high-level or cognitive capability of humans to reason and to think. 60 years later, however, high-level reasoning and thought remain elusive. The developments which are now being called AI arose mostly in the engineering fields associated with low-level pattern recognition and movement control, and in the field of statistics, the discipline focused on finding patterns in data and on making well-founded predictions, tests of hypotheses and decisions. Indeed, the famous backpropagation algorithm that was rediscovered by David Rumelhart in the early 1980s, and which is now viewed as being at the core of the so-called AI revolution, first arose in the field of control theory in the 1950s and 1960s. One of its early applications was to optimize the thrusts of the Apollo spaceships as they headed towards the Moon. Since the 1960s much progress has been made, but it has arguably not come about from the pursuit of human imitative AI. Rather, as in the case of the Apollo spaceships, these ideas have often been hidden behind the scenes, and have been the handiwork of researchers focused on specific engineering challenges. Although not visible to the general public, research and systems building in areas such as document retrieval, text classification, fraud detection, recommendation systems, personalized search, social network analysis, planning, diagnostics and A/B testing have been a major success. These are the advances that have powered companies such as Google, Netflix, Facebook and Amazon. One could simply agree to refer to all of this as AI, and indeed that is what appears to have happened. Such labeling may come as a surprise to optimization or statistics researchers, who wake up to find themselves suddenly referred to as AI researchers. But labeling of researchers aside, the bigger problem is that the use of this single, ill-defined acronym prevents a clear understanding of the range of intellectual and commercial issues at play. The past 2 decades have seen major progress, in industry and academia, in a complementary aspiration to human imitative AI that is often referred to as intelligence augmentation (IA). Here computation and data are used to create services that augment human intelligence and creativity. A search engine can be viewed as an example of IA. It augments human memory and factual knowledge, as can natural language translation. It augments the ability of a human to communicate. Computing-based generation of sounds and images serves as a palette and creativity enhancer for artists. While services of this kind could conceivably involve high-level reasoning and thought, currently they don't. They mostly perform various kinds of string matching and numerical operations that capture patterns that humans can make use of. Hoping that the audience will tolerate one last acronym, let us conceive broadly of a discipline of intelligent infrastructure, too, whereby a web of computation, data and physical entities exists that makes human environments more supportive, interesting and safe. Such infrastructure is beginning to make its appearance in domains such as transportation, medicine, commerce and finance, with vast implications for individual humans and societies. This emergence sometimes arises in conversations about an Internet of Things, but that effort generally refers to the mere problem of getting things onto the Internet, not to the far grander set of challenges associated with these things capable of analyzing those data streams to discover facts about the world, and interacting with humans and other things at a far higher level of abstraction than mere bits. For example, returning to my personal anecdote, we might imagine living our lives in a societal-scale medical system that sets up data flows and data analysis flows between doctors and devices positioned in and around human bodies, thereby able to aid human intelligence in making diagnoses and providing care. The system would incorporate information from cells in the body, DNA, blood tests, environment, population genetics and the vast scientific literature on drugs and treatments. It would not just focus on a single patient and a doctor, but on relationships among all humans, just as current medical testing allows experiments done on one set of humans or animals to be brought to bear in the care of other humans. It would help maintain notions of relevance, provenance and reliability, in the way that the current banking system focuses on such challenges in the domain of finance and payment. And, while one can foresee many problems arising in such a system, involving privacy issues, liability issues, security issues, etc., these problems should properly be viewed as challenges, not showstoppers. We now come to a critical issue: is working on classical human imitative AI the best or only way to focus on these larger challenges? To be continued.